Welcome back to another episode of Dominic Does DIY. Don't forget to click subscribe and share, and thanks to all those that have subscribed and come back to watch the episodes. If there's something I can improve or something you'd like to see more of, let me know down below in the comments. Today we'll do another boss's challenge. We'll see how well y'all can think on your feet. So the boss comes in and says, we had a machine go down on the line. The repairman can't come in for another couple days. We need a quick fix. The issue is our motor is down that runs the oiler of one of our CNC machines. We reviewed the operating data and it seems the motor runs on 12 volts and draws about 2 amps 100% of the time. The tech in the shop tried to connect 12 volts directly to the motor, but when he did that, it seemed like the system went into overdrive, pulling 6 amps and sprayed oil all over, making a mess. So we need you to make some fancy electronic control circuit to make it run right. And since you're doing it, be sure it has a switch. You look around your office and you know a simple FET to ground controlled by a switch will not work. That is no better than the tech connecting 12 volts directly. We could PWM it, but the firmware guy is nowhere to be found and you don't have time to deal with programming firmware right now. Looking around the lab, you find a switch, some resistors, a PNP, specifically a 2SAR542P, and an NPN, a 2N3904, and an LM7805. So what we have to work with, we have a switch, a PNP, an NPN, and some resistors, and we have a drive current that we need to regulate at 2 amps for the motor. Pause the video now if you would like to try and solve it. So let's go ahead and get started. Since all we have are BJTs to work with here, these are current-driven devices. We can take advantage of this. The problem with them is they have a real wide gain range, not only from component to component, but the gain can change depending on how much current is being passed. So it's not even easy to regulate at a component level for a single device. So here I'm using my motor control simulation again. So let's see what happens with my motor if I just put 12 volts directly across this thing. So you can see if I put 12 volts directly across the motor, we end up with about 6.66 amps, which is what the boss was saying. It says if we just connect it directly to 12 volts, the motor goes into overdrive and it pulls 6 amps and sprays oil all over the place. So we need to be able to regulate this current down to 2 amps. So for simplicity's sake, let's first take a look at the NPN transistor and see if we can just pull the motor to ground. So if we can do that, then it's very simple. We just throw this in there, control the base current, and then we are good to go. However, when we look at the data sheet for the 2N3904, this is just a general purpose transistor, and we cannot push 2 amps through this thing. You can see here the collector current, the IC, it has a maximum rating of 200 milliamps. So there's no way that we'll be able to pull the 2 amps required to run this motor through this particular transistor. But that is okay because not only do we have this NPN transistor, but we also have the PNP transistor. So let's take a look at the PNP transistor, the 2SAR542P. So when we take a look at this transistor, we can see that this one definitely has the capability to push the 2 amps we require. It has a collector current limit of 5 amps. So this is plenty good enough to be able to handle what it is that we need to do. So how do we now design for this PNP to push 2 amps? Well, if you remember back in the day of studying BJT, what is it? It's the IC, the collector current, is equal to the gain of the BJT times the base current. So let's take a look and see what the gain profile of this particular IC is. So taking a look at the HFE graph here, the DC current gain versus collector current, we can see that it actually is a pretty decent BJT. It looks like the curve is pretty much flat up to about 1 amp, but at about the 1 amp, it starts to knee off. And remember, we are trying to push 2 amps here. So when we look at this graph, we can see that at the 25C marker for a 2 amp collector current, we get a gain of about 225 is what I'm guessing based on this chart. Could be a little more, could be a little lower. I'm just throwing a number out there right now. So as stated earlier, our collector current is equal to the gain times our base current, and we need to know what our base current is to be able to push the 2 amps on the collector. How do we calculate that? Well, the base current is just going to be our collector current divided by our gain of the chart right there. So 2 amps divided by 225 equals about 8.89 milliamps. So now we have that PNP in there. We have my motor connection there on the collector of the PNP. And coming out of the base, I'm just using a constant current source that I've set to 8.89 milliamps to be able to drive that PNP to the desired current. So now if we simulate this, my collector current is now going to be controlled by my base current. And instead of getting 6.6 amps that we had earlier, that you see right there, when I run the simulation, it'll drop it down to roughly about 2 amps. So let's go ahead and run the simulation. So you can see here, now that we've actually controlled the current with this base current with the PNP, our current maximum dropped from 6.6 amps, it dropped down to 2.35. But we did want 2 amps and not 2.35 amps, right? So let's just go ahead and tweak this a little bit because that was reading the data sheet and that logarithmic graph and then just trying to assume the gain on that one. So now that we're just kind of close, now we can just tweak it a little bit. And if we go down to 7.25 milliamps and run that one, that puts us right around our 2 amp marker. So we'll go ahead and use that. And we will say, okay, for us to run this application, the PNP, we need a base current of 7.25 milliamps in order to drive this motor at 2 amps. Since we have a hard switch available, we can do some simple switching and just put a base resistor to ground using the switch to disconnect that base resistor from the ground source. So the switch would go between the 1.6K resistor and ground. So you can see how we calculated the base resistor to ground. It's just the VCC minus the 0.7 volts EB diode divided by the base current that we desire to have. So basic Ohm's law. So 12 minus 0.7 divided by 7.25 milliamps gives us 1.6K. Now let us go ahead and run this and see that it does indeed do exactly what we want. So you can see now we got 1.98, pretty much 2 amps going through our motor, which is exactly what we want. So pretty much it is done. Right, we have solved the boss's challenge at this point. We didn't need to use the NPN, nor did we need to use the 7805. But as a bonus, because we did have an NPN, I threw the LM7805 in there because I thought I was going to need something else, but I technically don't because I can just use the VCC rail, so I didn't need to drop it down to 5 volts. But regardless, the NPN, there is a way that we can still use that. Like let's say we wanted to drive this with a microcontroller, then the 7805, that would be the representative of the microcontroller output, but we really don't need that here because it would be a microcontroller that we would be using. So how do we use the NPN? Well, now we're not trying to push the 5 amps or the 2 amps for the motor, right? Now we just need to be able to drive this 7.25 milliamps. So let's take a look now. Let's go back to the data sheet for the NPN transistor. And so in the 2N3904 data sheet, we're going to take a look at the gain chart. And here you can see, remember we want about 7.25 milliamps. So looking at this chart, we can see at about 7.25 milliamps, our gain is about 150. So now let's go do the math and find out what our base current needs to be for the NPN in order to drive the collector with 7.25 milliamps. So here we can see 7.25 milliamps going through the collector divided by 150 gain means we need about 48.3 microamps going for the base. So then what does our base resistor got to be? Well, we have our 12 volt VCC minus our VBE of 0.7 volts over 48.3 microamps, and that gives us about 234K resistance. So we have a 234K resistor going up to VCC, and this time our switch would be put in between the VCC and the resistor in order to make it operate. Or with this one, we could actually, since our base current is 48.3 microamps, we could easily control this with a microcontroller if we wanted to. But for this one, since all we got is a hard switch, we just put the switch between the resistor, R4 here, and VCC. So let's run this one. And there you can see we get 1.97 amps going through the system using both the PNP and the NPN. Now they call this connection of the two BJTs, if you remember from class, kind of like a Darlington pair arrangement. I put the resistor in there, that R8, that 1.6K, I left it in there. So you can do this without the 1.6K resistor there. The only difference is you got to recalculate your gain because your VCE is now going to be different. So I'll leave it up to you to go research what happens if you short across R8 and you turn it into an actual full-on Darlington pair. But for now, that's it for the boss's challenge. We were able to successfully, based on a switch, force the motor to drive 2 amps, even though if we connected it directly up, it would want to pull 6.6 amps. So I hope you enjoyed it, and like, subscribe, and I'll see you next time. Thanks for watching.